Hello everybody. As you can see, I am now back at home from Arkansas. Had a good trip. We made the trip back home on Sunday. It was a long 11-hour trip, but both girls did pretty well with the trip. So Maya, the new baby, basically just slept the whole time. So it was really nice. We made it all the way home in one day. Good news. Today's lesson is the very last new piece of content that you will receive all year. This is lesson 11.7, and after today, that's it for the chapter. So Wednesday we're going to review, and Friday we're going to take our very last test of the year. So that's pretty exciting. So let's go ahead and get into it. Our objective for today is to graph rational functions. Okay, so inverse variations are examples of rational functions. A rational function, sorry, that's supposed to be underlining, can be written in the form f of x equals polynomial over polynomial where the denominator cannot be 0. Now that's important. This denominator, remember, this denominator cannot be equal to 0. Okay. We're going to need that bit of information here in a little bit as we are determining how to graph these rational functions. Okay, so to graph a rational function, f of x, you need to understand the graph's behavior near values of x where the function is undefined. Any value for the variable that makes the denominator of a rational function equal to 0 is an excluded value. Now this first problem here isn't really anything new. You guys know how to find the excluded values for functions like these, right? Excluded values are the value for x that makes this bottom equal to 0. Okay, so I've got x minus 2. What does x need to be so that this bottom is equal to 0? Well, to figure this out, we just add 2 to both sides, and we get x equals a positive 2. Okay, right? If I put 2 in here for x, 2 minus 2 is 0, and we can't have that, right? You can't divide by 0, okay? Because if you have 0 on the denominator of your fraction, that makes the whole function undefined. Okay, so the excluded value here for this first one is x equals 2. That's the excluded value. Okay, let's look at b. We've got y equals negative 3 over x plus 8. What would x have to be to make the bottom equal to 0? Well, x would have to be equal to negative 8, because negative 8 plus 8 equals 0. Okay, that's an excluded value. Now, why are we doing this, you might ask? These excluded values are going to help us. I think in the last lesson I talked about asymptotes for a graph. Okay, these excluded values are going to help us determine where the asymptotes are, okay, for our graph. Okay, so what I want you to do is go ahead and try the got it here down at the bottom. See if you can do it on your own. Determine what the excluded value for y equals 3 over x plus 7 is. Go ahead and pause the video. Okay, so for this, the excluded value has to be x equals negative 7, right? Negative 7 plus 7 is 0. Okay, now if we kind of go over to this next part here, we can see where these excluded values come into play. So the graphs of many rational functions are related to each other. Compare the graphs below of y equals 1 over x. Okay, so here we've got y equals 1 over x. The excluded value here would be x equals 0, right? Okay, what this does is this tells you, so if on the graph x equals 0 is just a vertical line at x equals 0. X equals 0 is this line, this vertical line right here. Okay, that's going to be what's called a vertical asymptote. Okay, a vertical asymptote. So basically, if you look at this first graph here, you notice that these two curved parts of this graph, both of them curve, and it looks like it slowly approaches this y-axis, but it looks like it touches it, but it actually never is going to quite reach it. Okay, the reason that it never quite reaches it is because x equals 0 is an excluded value. Okay, so it's going to get close and close and close and close and close to 0, but it's never going to quite reach 0. That's why it's an excluded value. It's called a vertical asymptote. Right? So like if you look at this fraction, you can have 1 over 0.1. You can have 1 over negative 0.1 or whatever. But you can't have 1 over 0, right? So you can get any value leading up to 0, but not including 0. Okay, so that's why we have a vertical asymptote here at x equals 0. Now let's look at this one right over here. Y equals 1 over x minus 3. What would our excluded value here be? For this one, it would have to be x equals 3, because 3 minus 3 is 0. Okay, now if we think about the graph of x equals 3, where's x equals 3 at? Well, you count over 1, 2, 3 spots. You're going to have a vertical line at x equals 3. That is our vertical asymptote. That's the point now where the graph, those two curved lines, okay, they're never going to quite get to x equals 3. They're going to have every value leading up to x equals 3, but it's never going to quite get to x equals 3. So both these graphs are identical in shape, but this second graph is just translated 3 units to the right. Okay? So notice that the graph of y equals 1 over x approaches both axes, but does not cross either axis. So we talked about the vertical asymptote, right? The line that goes up and down that it approaches. But we didn't talk about the horizontal asymptote. We didn't talk about this horizontal asymptote, right? There's also a horizontal asymptote at y equals 0. Okay, so think about this fraction right here, 1 over x. Is y ever going to be equal to 0 here? Is there anything I can plug in for x here to make y equal 0? No, because there's no value for x on top of the fraction. Okay, there's something I could plug in for x to make y equals undefined, but there's nothing I can plug in for x to make y equals 0. Because 1 divided by something, 1 divided by any number other than 0, is always going to give you a number other than 0, right? So that makes this y equals 0 also an excluded value. Okay? So we've got a vertical asymptote here and a horizontal asymptote here. Same thing for this one, right? There's nothing I can plug in for x here to make y ever equal to 0. So there's also a horizontal asymptote here at y equals 0. Okay, so there's two asymptotes, a vertical and a horizontal. Okay, so a line is an asymptote of a graph if the graph gets closer to the line as x or y gets larger in absolute value. In the graph of y equals 1 over x minus 3 above, the x-axis and the line x equals 3 are asymptotes. When the numerator and denominator of a rational function have no common factors other than 1, there is a vertical asymptote at each excluded value. Okay, so problem 2, using a vertical asymptote. What is the vertical asymptote of the graph of y equals 5 over x plus 2? Graph the function. So, first of all, vertical asymptote. Vertical is the up and down line. Okay, so you want to figure out what the excluded value is here. Here, we know that our excluded value is at x equals negative 2, because negative 2 plus 2 is 0. Okay? Now it says to graph it. So first, we know that we're going to have a vertical line at x equals negative 2. So if we come over to our graph here, here's our origin. We're going to go over 2 to the left at negative 2. We're going to have a vertical line. And usually we dot our asymptotes. Okay? Just to show that these are excluded values. Now to get the rest of the graph, remember you want to set up a chart, a table for these and plug in values, right? So you can plug in, so if our our vertical asymptote is negative 2, let's just start first going numbers bigger than negative 2. So we can go negative 1. If we plug in negative 1 into our function, negative 1 plus 2 is 1. So then 5 over 1 is just 5. Okay, you can do that for all of these values. So if we plug in 0, 0 plus 2 is 2, 5 over 2 is 2.5. Okay, each of these points, then we can come over and plot them. So -1, 5 is this point right here. 0, 2.5 is this point right here. If we plug in 3 for x, 5 over 3 plus 2. 3 plus 2 is 5. So 5 over 5 is just 1. So 3, 1, that point's right here. So that gives us this curve right here. Now we also want the curve that's on the other side, right, in the opposite quadrant. So now we're going to go for values of x that are less than the vertical asymptote. So let's start at -3. Plug -3 in for x. -3 plus 2 is -1. 5 over -1 is -5. So we're going to go with -3, which is right. Where's -3? That's -4. Oh, here's -2. So -3, -5 right here. Okay, then the rest, we've got -4, plug that in, you get -2.5 right here. Okay, -7, -1, and that gets us our other curve. Okay, so we've got a vertical asymptote here at x equals -2, and then our horizontal asymptote also is going to be at y equals 0. Y equals 0. That's this line right here. Okay. All right, I want you to go ahead and see if you can try to graph this on your own. Don't just skip over this, guys, because there will be questions about this on the test on Friday. So really try and work on this. See if you can figure this out. See if you can graph this on your own without any help. Okay, see if you can graph this to make sure that you're understanding it. Okay, pause the video, and then once you're done, come back and I'll show you how to do it. Okay, so first we got to figure out what our excluded value is for our vertical asymptote. Here, x equals 6. So we're going to go over 6. So 1, 2, 3, 4, 5, 6. And let's go by 2s actually. So 2, 4. We'll say that this is 6 right here. This is our vertical asymptote right here. Now, we want to set up a table of values. So let's set up our table here. Okay, so if I plug in 6 here, that gives us undefined. Now let's just try, let's plug in 7. Okay, 7 minus 6 is 1. -3 over 1 is -3. So our next point here is going to be 7, -3. Right here. We're going by each hash is 2. Okay. Next, let's have x. Let's go with 9. Okay. Plug 9 in for x. 9 minus 6 is 3. -3 divided by 3 is -1. So 9 would be right here, and then -1 gives us right here. And then let's just go with one more value. Let's say 12. 12 minus 6 is 6. -3 over 6 is -1/2. Okay, so let's see, 6, there's 12, -1/2 is about right here. So you can see we've got a curve. Oh, it's hard to draw these with a mouse, like that. Okay, now let's go to the left of our vertical asymptote. So let's just go with, let's say 5. 5 minus 6 is -1. -3 divided by -1 is a +3. So 5, 3. So 5, 3 is going to be right here. Okay, let's go with, let's say 3 for the next one. 3 minus 6 is -3. -3 divided by -3 is a +1. So the next point is going to be at 3, +1 right here. Okay, and then we can do one more. Let's just say we plug in 0. 0 minus 6 is -6. -3 divided by -6 is a +1/2. So we're going to have a point then at 0, 1/2, and then we can draw in our line, our sloppy line like that. So we've got two asymptotes here. The first one is x equals 6. The second one we know is y equals 0. That's our horizontal asymptote. Okay. Now compare the graphs and asymptotes below of, again, we've got y equals 1 over x. Okay, this is kind of like our parent function here for these type of rational functions. That gives us this right here, okay, where you have vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Now let's look at this one. Here we've got y equals 1 over x, but then at the end we've got plus 3. Okay, what this does is this actually changes the horizontal asymptote. It's going to actually move our graph up 3 units. Okay, so you can see how it affects our graph here. Our vertical asymptote doesn't change, right? X is still 0 here for our undefined value. Our horizontal asymptote, though, goes up 3 units by adding 3 at the end. Okay, what do you think is going to happen if we subtract 3 at the end? Yeah, the graph's going to go down 3 units. Okay, so the graphs are identical in shape. Nothing changes about the graphs. The only thing that changes is that it's translated 3 units up. Okay, so for a rational function of the form y equals a over x minus b plus c, there is a horizontal asymptote at y equals c. So here's what I want you to do. I would like you to take notes on this slide specifically. Okay, the graph of a rational function in the form y equals a over x minus b plus c has a vertical asymptote at x equals b and a horizontal asymptote at y equals c. Okay, so first, so for the vertical asymptotes, you're looking at the bottom part of the fraction here. X, the vertical asymptote is whatever x needs to be to make the bottom equal to 0. Okay. The horizontal asymptote is going to be whatever this is. So if it's plus something, it's a positive horizontal asymptote. If it's minus something, it's a negative horizontal asymptote. So in our first example right here, we've got a vertical asymptote at x equals negative 4, right? Because negative 4 plus 4 is 0. And we've got a horizontal asymptote at positive 1. Okay? All right, problem 3. It says, what are the asymptotes of the graph of f of x equals 3 over x minus 1 minus 2? And then it says graph the function. So our vertical asymptote is going to be x equals 1. Our horizontal asymptote is going to be y equals negative 2. Okay, pretty simple to figure that out, I think. Now to graph. First we make a table of values. Okay, so you can start at 0. Okay, we can sketch the asymptotes after we figure out, we plot these points from the table. We can just come over here and plot them in a graph. Okay, and you can see what it would look like. Okay, we've got our asymptotes right here. Both of our asymptotes now have moved here, right? Neither of them are on either the x or y axis. Okay. All right. What I want you to do is I want you to go ahead, plot the asymptotes for this function, and then graph it. Pause the video. All right. So we've got a vertical asymptote at x equals negative 3. We can plot that first. So we're going to come 3 over here. It's kind of sloppy, but and then a horizontal asymptote at negative 4. So down 4 right here is our horizontal asymptote. Okay. And now to graph them, okay, we set up a table of values. We can just start with, let's say we start with 0. 1 over 0 plus 3 is negative 1/3. Minus 4 is negative 4 1/3, right? So 0, negative 4 1/3 is going to be like right there, I guess. Okay. Let's say we try, let's say we do negative 3. How about that? No, we can't do that. Negative 4. Let's try negative 4. Okay, if we do negative 4 plus 3, that's negative 1. Negative 1 divided by negative 1 is a positive 1. And then 1 minus 4 is negative 3. So we got a point at negative 4, negative 3 right here. Okay. Let's say we do negative 5. Why not? Negative 5 plus 3 is negative 2. Negative 1 divided by negative 2 is a positive 1/2. And then 1/2 minus 4 is negative 3.5. So negative 5, let's see, is right here, and the negative 3.5 is right here. So you can kind of see already, you're going to get this shape looking like this. And then our other side, we can just kind of plug in. It's going to look something like that. It doesn't have to be perfect. Okay, but you can kind of see based on the asymptotes what the graph is going to look like. And I'm going to show you something here in the next problem that's going to make this a little bit easier too. I think it's this. Yeah, it's this problem. Okay, last problem. Using a rational function. Your dance club sponsors a contest at a local reception hall. Reserving a private room costs $350. And the cost will be divided equally among the people who enter the contest. So basically, $350 reserves the room, and then that cost is split between all the different people that are participating in the dance contest. Then each person also pays a $30 entrance fee. So part A here says, what equation gives the total cost per person, y? So y is the total cost per person of entering the contest as a function of the number of people, x, so x is the number of people who enter the contest. So let's think about this. First, this $350 is being divided by the number of people. It's being split up between all the different people that are participating in the contest. So y equals, right, y is the total cost per person. So the cost per person is $350 divided by the number of people, but then there's also a $30 entrance fee, so we got to add 30 here at the end. Okay, this is the function that we're going to be using here. Okay, this is the equation that gives the total cost per person who enters the contest. Now, part B says, what is the graph of the function in part A? Use the graph to describe the change in the cost per person as the number of people who enter the contest increases. So, I mean, we could very easily set up a table for this, right? And just manually graph it. Or we can kind of use Desmos to help us out here. Let me open it up over here. So, I'm going to go ahead and enter in our equation. Our equation was y equals 350 divided by x plus 30. And you can see it gives us a graph that looks like this. Okay. So it says, use the graph to describe the change in the cost per person as the number of people who enter the contest increases. If we go back over here, you can see from this graph that as the number of people who enter the contest increases, right, as we get more and more people here, the cost per person decreases, right? Y represents the cost per person. As more and more people enter the contest, this cost gets lower and lower and lower. Okay. We don't really want to pay attention even to this side, the left side of the graph, for this example, because you can't have negative people entering the contest, right? So this left side of the graph is really irrelevant here. Okay. So because the horizontal asymptote here is at y equals 30, right? The cost per person will eventually reach $30, but again, it's never going to quite reach $30 exactly, right? Unless they decide to just waive that $350 room fee, right? All right. Last part here says approximately how many people must enter the contest in order for the total cost per person to be about $50. What we can do is we can come over to our graph here and figure out how many people need to enter the contest for it to be $50. So if we come over here and plot a point here at about 50, let's see. Actually, what we can do is let's do y equals 50 here. Let's plot a line here, and then we should be able to see right here there needs to be approximately 17.5 people. So like 17 or 18 people need to be there or need to participate for the total cost to be about $50. Okay. All right. So that's how you use Desmos for these types of things. Basically, this slide just gives a summary of all the different types of functions that we've learned about this year. We've talked about linear functions. Y equals mx plus b gives us straight lines. We've talked about quadratic functions. That's when you have an x squared in there. It's going to give us a parabola, right? We've talked about absolute value functions where it's going to be shaped like a V, right? We've talked about exponential functions where you have x as an exponent. It's going to be something like this, like an upward slope. We've talked about square root functions where you have a square root. It's going to be something kind of like this shape. And then finally, we've talked about rational functions. That's where you get opposing curved lines like this with two asymptotes. Okay? All right, so your assignment for today is on Math Excel. This is the last Math Excel for the year. If there's any part of this lesson that you didn't understand, you can feel free to email me. I will be having my live Q&A since I'm home. I'll have that Q&A on Friday again, so that you can feel free to ask questions about this assignment, any other assignment, or actually you can even use that time to ask questions in preparation for your test as well. Okay. So if you have any questions before Friday, don't hesitate to just send me an email. I'm happy to answer them. All right. I hope you guys have a good day, and we'll see you guys later. Bye.